All right, temperature. How do you measure? How do you define temperature? Middle school, high school, they define it as temperature is the hotness or coldness of an object. Hotness or coldness of an object. I don't like that definition because when you really look at what's happening, if you heat a substance, let's say you're heating a solid, the molecular vibration increases, right? So the kinetic energy of every molecule increases, but each molecule does not have the same kinetic energy, do they? No. Therefore, you'll have to talk about the average kinetic energy of the molecules increasing. Therefore, temperature is a measure of the average kinetic energy of molecules. That is the definition. The definition. Temperature is the average kinetic energy of the molecules. This is chapter 17. And whenever you try to measure temperature, you have to have a scale. So there are three scales. There are more than three, but we'll talk about three scales. In all the scales of temperature, the lower fixed point and the upper fixed point are the same. The lower fixed point is the melting point of ice at 1 atm. The upper fixed point is the boiling point of water at 1 atm. So the melting point of ice and the boiling point of water. On the Celsius scale, or the centigrade scale, as it was called back then, this is taken as, on the Celsius scale, is taken as 0 degrees Celsius. So the melting point of ice is 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. But on the Fahrenheit scale, the melting point of ice is 32. The boiling point of water is 212. On the Kelvin scale, it's 273. That's the melting point of ice. 373 is the boiling point of water. So there you see the difference. Another thing that you should notice is this gap here, the space is divided into 100 parts. Easy to understand, 100 parts. But here it's divided into 180 parts. That's the difference, right? 212, take away 32. Here again, it's divided into 100 parts. Therefore, it's very easy to convert from Celsius to Kelvin. I know you've done it multiple times. To change from Celsius to Kelvin, all you got to do is add 273. Right? To be perfect, it's actually 273.15, but you always add 273. That's how you change from Celsius to Kelvin. How do you change from Celsius to Fahrenheit? Let me just give you an example and check it out without giving any formula. 50 degrees Celsius. Use the information on the screen, think about it, and tell me, 50 degrees Celsius is how many Fahrenheit? So, before we go to the equations, just take a look at this. This is extrapolated onto the negative side. Now, this is what we were talking about, freezing point of water, 32, 0, 273. If you go to the lower side, you see that on the Fahrenheit, absolute zero is that much, negative 459.67, negative 273.15 on the Celsius scale, of course, absolute zero. Now remember, there are no negative temperatures on the Kelvin scale. That's why it's called absolute zero. That is the lowest temperature possible, absolute zero. And practically, we've got very close to it. We're like 0.19 degree away the last time I read about it. We've got very close to absolute zero, practically. Theoretically, according to Kelvin, and we're going to look at it, Kelvin proved theoretically that you cannot have a temperature lower than 0 Kelvin. We'll get to that in the final chapter from now. But this is the ready-made equation that you use to convert. All right. Same thing, 9 by 5 is 1.8, right? Okay. So those are the two equations. This is the third one. And I've put some examples there. 100 on the Celsius scale. Now, this is an interesting one. I picked negative 40. Just look at this. on the Fahrenheit if it's negative 40? And I'm trying to change it into Celsius, right? Subtract 32, multiply by 5 by 9, correct? Surprising enough, the answer would be negative 40. Now that's the only temperature at which both are equal. So negative 40 on the Fahrenheit is equal to negative 40 on the Celsius. You never thought that possible, right? But they are the same. That's the only temperature at which they are the same. That's why I picked that. That's why I've written here. Okay. Well, of course, Celsius to change to Kelvin. And I told you, no negative temperatures are possible on the Kelvin scale. So that's about the temperature scales. Well, you can't see these numbers, but the magnitude of the temperatures in the universe goes from 10 to the negative 30 to 10 to the positive 13 Kelvin. The range of temperatures in the universe. What's the temperature of the sun? What's the temperature of the sun? At the core of the sun, at the center of the sun, it's 10 million Kelvin. Accurately calculated, knowing the thermal conductivity of the gases, hydrogen and helium, which the sun is made of, right? 10 million Kelvin. But at the edge of the sun, from where it's radiating heat and light, it's only 6,000 Kelvin. At the center, 10 million, and at the edge of the photosphere, it's 6,000 Kelvin. You know, what is the meaning of the word thermodynamics? Thermal, heat. What's dynamics? Dynamics is movement, motion. Using heat to move. Converting heat into mechanical energy. That's how you reached the college this morning. Tiny explosions in the engine, right? Those are explosions. And the heat produced was being used to drive you here, believe me. So that's what this is all about. But you know, when you get, and this big chapter is based on 4 laws. But when they got the first law, of course, they called it the first law. But then they got a law that was more fundamental than that. They could not call it the second. They called it the zeroth law. That's the story. Okay, so there is the zeroth law, the first, the second, and the third law. We'll look at all those in the chapters to come. But the zeroth law is very fundamental. It says if you have 2 systems, well, what's a system? A system could be a gas in a container or a mixture of gases. So if you have 2 systems, A and B, and let's say that they are both individually in thermal equilibrium with a third one. So A is in thermal equilibrium with C, B is in thermal equilibrium with C. Definitely A and B are in thermal equilibrium with each other. But now what's the meaning of the word thermal equilibrium? That means that temperatures are equalized, that's all. Another point, if they are not in thermal equilibrium, that would mean that heat would flow one way or the other until they reach equilibrium. That's the zeroth law of thermodynamics. That's clear, right? So it gives us an idea of what temperature is. So it says, the statement is if 2 systems are in thermal equilibrium with a third one, then they are in thermal equilibrium with each other. That is the zeroth law of thermodynamics. The significance is that the temperatures are equal. When you put down that word, that means the temperatures are equal. That's what it means. Oh, stop. That picture represents a bridge on the left side. What's this? Isn't it easy to understand why there should be gaps like that? Because otherwise in summer when it expands, what happens? When it expands, there's no space for it to expand, so there will be a lot of thermal stress that builds up and the bridge buckles. So, and haven't you seen gaps left in the railroad? Haven't you? Yeah, huge gaps. Now, why should there be huge gaps? Because the original length is bigger. Remember, one railroad, a piece of the railroad is big, right? So what am I trying to say? I'm trying to say that expansion depends on the original length. If you have a 1 meter rod of aluminum and you have a 2 meter rod of aluminum, same material, the 2 meter rod is going to expand double the 1 meter rod when heated through the same range of temperature. Now, already I told you that expansion depends on three quantities. Did you hear me? Expansion, linear expansion, depends on three quantities. One, it depends on the material. Two, it depends on the original length. Three, it depends on the change in temperature, correct? You got that? We could put all those three together and get an equation. Change in length is equal to the original length times alpha times delta T. That's the original length. That's the change in temperature. Alpha is a constant. It's called the coefficient of linear expansion. The coefficient of linear expansion. In fact, today in the lab, I've set up another lab where we're going to find the coefficient of linear expansion of 4 different materials and compare them. Right? You're going to compare them. 4 different metals. And then you will see what we're talking about. So that's the formula that is coming up. Change in length. And you have all those quantities. The original length, the constant, and the change in temperature. On the right side, what you see is a bimetallic strip. There are 2 metals that do not expand equally. All right? They are riveted together, stuck together, they won't separate. When you heat them, this is what's going to happen. Look at the diagram and tell me quickly which metal expands more. I mean, that's easy. The blue or the yellow. Which one expands? Which one has a higher coefficient of linear expansion? The blue one. Why? Because you can see that it's bending inwards because this one tries to have a greater length. And this one is definitely a little bit smaller when it bends that way, right? Now the question is, if you cool it, what would happen? If you cool it from here, what will happen? Will it bend the same way or will it bend in the opposite direction? Yeah, I heard it won't bend. It will surely bend. It will bend. See, remember that the one that expands more is going to be the one that contracts more. That's a law of nature. The student who listens more gets a higher grade. The object that absorbs more emits more. It's true. A black color object absorbs heat, correct? And if you have a black object with a white object at the same temperatures, which one do you think will emit more heat on the basis of what I told you right now? Black one. That's why I said it's a law in physics, it's a law of nature. Whatever absorbs more emits more in class 2. So which one is going to contract more? The blue one. So definitely it has to bend the opposite way, because the blue has to have a smaller length and the yellow has to have a bigger length, correct? You got it? Now this is the device that we use to automatically switch on and off any electrical device. What's it called? A thermo switch. An automatic iron, for example. An automatic iron. You switch it on, it goes off, right? How does it know? Because of this device. The thing is, there will be an electrical connection here. And when it gets too hot, the electrical connection stays here, This one bends off. You see there's a break in the circuit. You see that? And then it begins to cool. As it begins to cool, what happens? It gets straight, and then it touches. Oh, again, the current flows, gets hot. That's it. Anything that is automatically switching on and off basically uses this. There are other systems. There are magnetic relays and all that, but this is basically what you use in a refrigerator. It switches on and off in an AC, air conditioner. Otherwise, it would have been terrible if you had to manually switch it on and off. And you forget, the whole house would be frozen, you know. Yeah. Okay. So that is expansion. But I don't know, did I? Let me ask you this question. I've not asked you. This is my favorite question. One of my favorite. Imagine that the door frame and the door are made of the same material. This is not wood, but just imagine this is also made of wood, right? And this door was put in place in spring, like now, in spring. And the one who made it exactly fitting. Just not too much of a gap. I question. In either summer or winter, this door is going to jam. But you got to tell me, without opening your mouth for a minute, think, is it summer or in winter that the door is going to jam? You know what I mean? All right, you have a... So in summer, both expand, all right? Isn't that what you told me? Both expand, right? So the door expands, the door frame also expands. Go on.
So the space between them will get...
Oh, the door frame also expands. Isn't that what you told me just now? The door frame also expands. The door expands. Which one expands a little bit more? Which one had a little bigger original length? The door is inside the door frame. The door is inside the door frame. Now, come on now. So originally, which one is a little bigger? Thank you, the door frame. Therefore, when they expand, which one will expand a little bit more? The door frame. Pedro, you're right. You got extra credit for today. So in summer, did you get that? In summer, both will expand. The door will, exaggeration, the door will expand that much. The door frame will expand that much. So there'll be a gap between them. Winter, both will contract. The door frame will contract more than the door. I told you, whatever expands more will also contract more. So in winter, it will jam. You got it. Now the next question is equally confusing. Thank you, I got you listening. You have a metal plate. You have a metal plate and a hole in it. You have a metal plate and a hole in it. Okay? That's not too difficult to understand. And when you heat it, I want you to think about it and tell me what happens to the size of the hole. And you have 1 minute. The size of the hole will increase. But the problem in our thinking is that we always think, but doesn't it increase inward? Doesn't it? No. The size of the hole will increase. And that's the only explanation I can give you to make you understand. If you draw a circle on it and heat it, the circle is going to get bigger, right? That's the logical explanation for that. One more thing. We have all seen horse carts. Haven't you? Horse cart? What are the wheels made of? Wood. But around the wood, what do you have? A strip of metal. Because if that's not there, it won't last too long. You know how they put it on there? Mm-hmm. Actually, the initial size of that ring or the hoop, whatever, is exactly the same as that of the wooden tire. It's the same. But they heat that ring to a very high temperature. What happens when they heat it? All right, you got it. It gets bigger. And while it's still hot, they put it on top of that. When it cools down, it shrinks and fits so tight that nobody will ever get it off unless you heat it back to that same temperature. That's how they fit it on. And actually, there is a process called, I don't know how many have heard about this process. How many? Okay. It's exactly the same thing. You want to combine two metal plates. You want to combine two metal plates, let's say. That's a silly drawing. Okay. Two metal plates. What you do is you make a hole through both of them. You take another metal, usually aluminum, because aluminum expands a lot. You will see that in lab today. And initially, this aluminum plug, will be slightly bigger than that hole. So they cool it. The plug is cooled. You can do it either way, Cool the plug. So what happens? When it's still cold, drive it into this. And when it gets back to room temperature, that's the tightest fit you can ever have. So expansion is any topic in physics is practically very useful. Expansion in particular is very, very useful. But when we talk about linear expansivity, that's like we're only talking about solids. Only solids have a length, right? So what about if we want to talk about the expansion of fluids, liquids and gases? Then we'll have to talk about volume expansion. Volume expansion and the formula is the same. The same formula. Change in volume is equal to original volume times beta times change in temperature. Beta is called the coefficient of volume expansion. But what you have to know is that beta is 3 times alpha. Beta is 3 times alpha. That's very important for you to know. It's the coefficient of volume expansion. Water is so special, isn't it? Water is special in many ways. All right, let's talk about this a little bit. When you heat any liquid, what happens to its volume? The volume of a liquid increases when you heat it, correct? That's why you have to be careful in summer when your fuel gauge shows empty. In summer, when your fuel gauge shows empty, remember that the gasoline inside has already expanded. It's summer, right? And the gauge system is a float system, you know what I mean? So it's expanded. So when it's showing empty, fill it up as quick as you can because there's not much in there. It's expanded. But in winter, it's okay. You can drive quite a few miles. You saw the difference? Summer is coming, so be careful. When it shows empty, and don't say, winter I could drive 50 miles. In summer you'll drive 35 miles. You'll be stuck on the road. Now you got it. Not every liquid expands when you heat it. Water is so strange that when you heat it, it contracts. I know you don't believe me. Not at all temperatures. Let's look at a piece of ice. The density of ice is 920 kilogram per meter cube. We've talked about this, that's why ice floats in water. We know that, right? Okay, you heat ice, what's going to happen? It'll melt. When it melts, do you know that the volume goes down? Yeah, that's why the densities are different. That's why in winter we've got to insulate the water pipes. Because there's water flowing, and if it freezes, when it becomes ice, what happens to its volume? It expands, and the metal pipes can crack. Whatever it is, it'll crack. If it's PVC, it'll crack even faster than that. So when you heat this, its volume decreases. So water at 0 degrees Celsius, the volume is less, right? Now start heating it. Continue heating it. 1 degree Celsius, the volume again decreases. 2, again it decreases, all the way up to 4 degrees Celsius. So if you draw a graph of temperature and volume, it'll look something like this, up to 4 degrees Celsius. Water has the smallest volume at 4 degrees Celsius. That means it has the biggest density at 4 degrees Celsius. Isn't that right? And that is the number that we use, 1000. That's actually the density at 4 degrees Celsius. So beyond 4 degrees Celsius, it's like any other liquid. When you heat it, what happens to its volume? It increases. Now that property is called the anomalous expansion. You have heard of the word, how do you say it? Anomaly? What do you mean by that? Means extraordinary, not usual, correct? Yeah. So look at the volume. The volume is decreasing. Now, please label 0 degrees Celsius here. And that's 4. So that's 0 degrees Celsius. Volume is higher. From 0 to 4, the volume is decreasing. Beyond that, it's increasing. So this is where the special property of water is.
Do they know why?
Do they know why? Well, I know why.
What?
Okay, wait, we'll get to that. Do they know why? It will always has good density. And the reason why we use 1000 at all temperatures is very clear. That's why I picked this graph. Look at the change. Is it so huge?
No,
Look at that. It's 999.5, correct? At 12 degrees Celsius. See that? So the change is not that much. Do you see that? It's because this is in gram per centimeter cube. It's 1. Well, that was supposed to touch. Anyway, it's 1 at 4 degrees Celsius. You see? Maximum density, 1, which is 1000. After that, the density falls. So now I told you. You know the story. Okay, gas loss. That's where our chemistry comes in. I'm going to test you nicely now. You know, when we look at a system, again, a container with a gas in it. This is not for 1 chapter. This is for 4 chapters, whatever I'm telling you now. What are human beings trying to do? What's our aim? When you look at something, what's our aim? Even when you look at a person, our aim is, what can I get out of him? It's true. It is true. When you look at a system, it's like, can I use it? Oh, is there energy in the system? And then we want to know how we can measure the energy. But we can't measure the energy in a system. But we could measure its pressure, volume, temperature, and entropy. These 4 are called the thermodynamic coordinates. Thermodynamic coordinates. What do you mean by a coordinate? In geometry, you know, coordinate, if you give the x and the y coordinate, you know where the point is. If exactly the same. If you know the numbers, if you know the pressure, volume, temperature, and entropy, you know how much energy is in there. Why should you know how much energy is in there? So you can tap it. So you can, and so that's thermodynamics. And entropy is dangerous. It's like love. Yeah, love is dangerous. It's an abstract noun. Can anybody define love? You can't. You can say, oh, it's the feeling that I need to sit with that person all the time. Well, you really did not define love. The same is the case with entropy. In chemistry, you've heard. Entropy is a measure of the disorder of a system. Memory is coming back? If you did take chemistry. So we'll talk about all that later on. For the time being, let's forget about entropy. There are 3 variables, right? There are 3 variables, and there are 4 gas laws. Throw them at me. Boyle's law.
Pressure and volume.
What's the relation between pressure and volume?
They're inversely.
Inversely. Wow, you make it easy for me. Inversely proportional, which means, easy, if you increase the pressure, what happens to the volume? Decreases. Therefore, mathematically, you will write it like this, wouldn't you? Inversely proportional. How do you change a proportional into equal? Multiplying with a constant. So you will go, that's a constant, 1 by P. Rearrange, pressure times volume is a constant. Boyle's law. And so you say P1, B1 is equal to P2 times V2. Simple thing. Therefore, if the pressure has increased 3 times, the volume has decreased 3 times. But that's not Boyle's law. Unless you give me the condition, which most students don't give.
all the other variables?
The temperature and the mass, constant. So you need to have a fixed mass of gas at a constant temperature. Are you listening? A fixed mass of gas at constant temperature. That's Boyle's law. All right. Give me Charles' law. There's Charles' law, there's Gay-Lussac's law. Have you heard of all the gas laws? There's Dalton's law of partial pressures. There's Avogadro's hypothesis. I'm going to tell them to you, don't worry. It's simple, it's simple. Look, you drive from here to Dallas because you hate physics. Anyway, you drive. So as you drive, what's happening to the temperature of the tires? Increasing, right? Come on, we're talking about the tires. It cannot expand. It's negligible expansion, right? So the air inside is trapped. The volume cannot change. Even if it changes, it's negligible. So what happens to the pressure? Goes up. So what was the constant here? Volume. So when the volume and the fixed mass of gas, because there's no extra air going in or going out, if your tires are good, it's not leaking, you know what I mean? So for a fixed mass of gas at constant volume, pressure is directly proportional to the absolute temperature. I use the word absolute temperature. Did you hear me? That means it has to be in Kelvin. I mean, this makes sense. Increase the temperature, the pressure goes up. Correct? All right, let me also show you the seriousness. This was a problem on the final exam. And all the students who sleep in class got it wrong. Sorry, it's being recorded, but it's okay. Now, let's say the initial temperature was 25 degrees Celsius and the pressure was 288. We'll keep it in atmospheres, the first and the last time. You have driven to Dallas, the temperature goes up to 40 degrees Celsius. It's summer, so it contributes to that. Find the new pressure, please, go. Find the new pressure. I gave you the formula. Pressure is proportional to temperature, isn't it? At constant volume. Take a look. That means P1 by T1 is P2 by T2. Agreed? Because when you do this, you're going to get P is equal to K times T. And so when you bring it over to the other side, it means P by T is K. So I want you to use that and find out the new pressure in 1 minute. Go. Volume is directly proportional to the absolute temperature when the pressure is constant. Okay, so you have the Boyle's law also coming out there. So I gave you the 3 equations. Shall we combine all the 3 and you will get the ideal gas equation? Hey, there's one equation that you know that I didn't have to teach you. Okay. All right, so the ideal gas equation. By the way, give me an example for an ideal gas. They don't exist. They don't exist. All gases are real gases. But the behavioral difference is so tiny. That's why we assume that all real gases are ideal gases. You see that? The word ideal means perfect gas. There's no perfect gas, but you can use this. What's the ideal gas law? PV is in RT. Okay, explain the terms. P
Pressure.
in
Constant.
pascals. I know in chemistry you take it in ATM. That's out the door here. It has to be in pascals. Volume in meter cube. Meter cube. What's N? Number of moles. Oh, we have a problem. With number of moles, we have a problem. We may not have it in this class. Let me ask you, what's 1 mole of oxygen? See, we have a problem. What's 1 mole of oxygen? Here. What is the symbol for oxygen? Is this a symbol for oxygen? No, I don't think so. Thank you. What's the difference? There are 2 atoms in 1 molecule of oxygen, right? And the molecular weight of oxygen is 32, not 16, 32. You heard me. 16 times 2, 32. So when you say 1 mole of oxygen, you're talking about 32 grams of oxygen. But we never use grams, so you'll have to say 0.32 kilograms. I hope that's clear. One more example. Nitrogen is written as N2. Again, it's diatomic. So N2, molecular weight, nitrogen. 28. So 28 grams of nitrogen is 1 mole of nitrogen. So what do you mean by 1 mole? 1 mole is its molecular weight expressed here in kilograms. You know what I mean? And what's so special? What is so special? Why do we have to talk about a mole? You know, if you can't enjoy this part, it's sad. Because if you look at it, all the gases, you know, the gases have so many different behaviors, don't they? We breathe in oxygen. Try breathing in hydrogen. You won't last long. It looks like these gases are totally different, correct? Right? But they are not. That is what Avogadro found out. Okay, save time. What is Avogadro's hypothesis? If I ask you for Avogadro number, I know you'll spin a big number at me. I know. All right, let's at least get that number. 6.022 times 10 to the power 23. You reduced it by 100? Okay. Times 10 to the 23. I'm not interested in this number. I'm interested in, can you tell me what that is? Somebody, what does that represent? Then I'll tell you that you did learn something in chemistry. Let's take it one by one, one by one. Who wants to go? David wants to go. Go.
The number of molecules in 1 mole of a given gas.
One. No, that's right. What he said is exactly right. So if you take 32 grams of oxygen, I'm happy. If you take 32 grams of oxygen, it'll have that many molecules. You take 28 grams of nitrogen, it'll again have. So they're not really so different. You see, any gas. Are you getting it? Any gas, 1 mole of any gas. I think you should write that down. 1 mole of any gas has these many molecules. 1 mole of any gas has these many molecules. 6.022 times 10 to the 23. But it doesn't stop there. Have you heard of STP? What's that? Standard temperature and pressure. What do you mean by standard temperature? 273 Kelvin. What is standard pressure?
180.
What did you say? 101,325 pascals in physics. No ATMs here, except when you want to get money out. Okay. So 101,325 Pascal. Okay. It doesn't stop here, you know, STP. If you take 1 mole of any gas, 1 mole of any gas, and keep it at STP, they will all have a volume of 22.4 liters. That's crazy. You take 1 mole of any gas, maintain the temperature at 273, keep the pressure at that, 101,325, measure its volume, it will be exactly 22.4 liters. Let me show you what I'm trying to talk about. What is the molecular mass of hydrogen? H2, right? H2, 2 grams. Wow. So 2 grams of hydrogen at STP will occupy 22.4 liters. 32 grams of oxygen will occupy the same. Now can you see that hydrogen molecules are smaller, lighter, and they fly around? They're able to occupy a bigger volume. Is anybody getting what I'm trying to say? So behavior-wise, they are fine, they're the same. They show the same type of behavior. Why did I have to tell you all the story? Otherwise, you will not work out problems. That's why. So N is the number of moles. Going back to this, caps R is called the universal gas constant. The universal gas constant means it's the same for all gases. It's the same for all gases. And the value, which you have to know, is 8.314, and the unit is joule per mole per Kelvin. Let me show you quickly how I get that unit. Does anybody know what pressure times volume is? It's work. Keep that in mind. Pressure times volume is Bernoulli's principle. Don't you remember? Okay, anyway, that's work. What's the unit of work? Joules. And this is per mole, isn't it? And this is what? Kelvin. So they went over to the other side. It's in the denominator. That's why it's joule per mole per Kelvin. That's the reason for the unit. All right. Now, what I'm trying to write here is, just look at this and tell me what's caps N. Oh, what's small n? Number of moles. That's Avogadro number. So what's this? Oh, what do you mean by Avogadro number?
Number of molecules.
Yeah, this is the total number of molecules. See, because Avogadro number is the number of molecules in 1 mole, isn't it? So if you multiply it with, let's say, 5 moles, you get the total number of molecules. There are too many n's coming in. You have to know what they stand for. Caps N is the total number of molecules. Na is Avogadro number. Small n is the number of moles. Let's take it further. You did not get it this way in chemistry, I know, but that's a simple math. And if you did not understand, I don't know how to explain that to you. That's simple math. You saw that. And then let's substitute it into the gas equation. You will agree, did you? Come on. Isn't this N? nRT? Now on the right-hand side, look carefully and tell me, do you see 2 constants? Do you see 2 constants on the right-hand side? What are the 2? The universal gas constant and Avogadro number, isn't it? If you divide them, you get what is called the Boltzmann constant. Okay, so we can represent it this way. Watch that. Simple substitution. I hope you understood. And the Boltzmann constant is 1.38 times 10 to the negative 23 joule per Kelvin. All I did is, come on, in place of this by Na, R by Na, I substituted K. Do you get it? Okay, that's all. So this is another way you can write the ideal gas equation. That's why I put them side by side. So you see that? You can either represent it this way or this way. What's the big difference? Number of moles, universal gas constant, total number of molecules, Boltzmann constant. Simple thing.